scenario here of two blocks that we're going to consider combining together into a system. Two blocks are pushed to the right so that they move together with increasing speed. Block B remains at the height shown. Ignore friction between the ground and block A, but not between block A and block B. The mass of block A is 10 kilograms and the mass of block B is 2 kilograms. Let system C represent the system consisting of both blocks A and B, and we're going to use the kinder, gentler version. Acceleration due to gravity, little g, is 10 meters per second squared. Part A, for block A, block B, and system C, we are to draw free body diagrams, identify any Newton's third law force pairs, so interaction pairs, and write out the algebraic form of Newton's second law of motion. So sum of the forces is equal to mass times acceleration. Alright, so let's see if we can do that. I want to start this process because it'll be more clear if we start with block B first. So block B is accelerating to the right, but it's not moving up or down. The block definitely has weight. So there's the weight. And then what cancels out that weight? It's going to be a force of static friction up, and block A is pushing into block B with some force, which I'll write as the force on B due to A. Alright. For block A, its free body diagram, I'm going to have some interaction pairs. So A is pushing forward on B, so B is pushing backwards on A. So we're going to have a force on A due to B. There is the weight of block A, and interaction partner to this force of static friction. So there's a force of static friction up on block B, so block B is going to exert a force of static friction down on block A, Newton's third law. So I'll just write that in as minus force of static friction. It's going to be equal and opposite to that force of static friction. The ground is going to exert a normal force up on A. Make sure block A neither jumps up in the air or falls through the ground. So the normal force on A cancels out both of those forces in the vertical direction. And then the hand is pushing the block to the right. I'll just call that force of the push. Okay, so what things are guaranteed to be equal and opposite from Newton's third law? We mark them with X's like we did before. So the force of static friction up on block B is equal and opposite to the force of static friction down on block A. And then the force of block A pushing block B to the right is equal and opposite to the force of block B pushing block A to the left. So that's going to be a normal force at that interface. All right. Now, I combine these two free body diagrams together to get the free body diagram for the system. And all of the internal forces to the system are going to cancel in pairs. So the force on B due to A and the force on A due to B, when I add these two free body diagrams together, that cancels out. Force of static friction up, force of static friction down, those cancel out. So everything together for the system, I'm going to have a normal force on the system. I'm going to have their combined weight, mass of A plus mass of B times the acceleration due to gravity, and then I have the external force from the push, F of the push. All right, writing out Newton's second law of motion for both the x direction and the y direction, so to the right and then up the page. From the free body diagram for A, I'm going to have force of the push is in the x direction, and the force on A due to B is in the negative x direction, and that is going to equal the inertia of block A times the x component of its acceleration. For the y vertical component, normal force on block A minus the force of static friction on block A minus the weight of block A is equal to 0. For block B, the force on B due to A is going to be the mass of block B times the x component of its acceleration. The force of static friction up is big enough to cancel out the weight of block B. And then for the system of both together, force of the push to the right is going to equal mass of block A plus mass of block B times the x component of acceleration. And in the vertical direction, normal force on the system is enough to cancel out the weight. MA plus MB times G. Pointing down. Okay. Using only the forces in your free body diagram for system C, calculate the magnitude of the force exerted on the system C by the ground. So we want to calculate this normal force on the system. Normal force on the system, I move those puppies to the other side. That's going to be mass of block A, mass of block B, times the acceleration due to gravity. And that's going to be 10 plus 2 is 12. 12 times 10 is 120 newtons. All right. Using only the forces in your free body diagrams for blocks A and B, calculate the magnitude of the force exerted on block A by the ground. So we want to find this. Okay. So what are some things that we are going to need? Since this has the force of static friction in it, I need to know how big that is. So first, the force of static friction is big enough to cancel out the weight of block B. So it's mass of B times acceleration due to gravity is 20 newtons. And then using the vertical equation, Newton's second law, the free body diagram for block A, we have the normal force on block A is going to equal force of static friction plus mass of A times acceleration due to gravity. We know how big this is. It's 20 newtons. So that is going to be 20 newtons plus 100 newtons. That is 10 kilograms times 10 meters per second squared. Is 120 newtons. And how should the value of the normal force on the system C and the normal force on block A compare, they need to be the same. And in fact, we see they are. Having a system is a choice that you make. The underlying physics doesn't know what you pick to be a system. Pick whatever is going to be most convenient. All right, last page. Now this is a little bit trickier. So I have acceleration in two directions simultaneously. All right, suppose the friction between the two blocks is reduced, so that block B slides down as the blocks move to the right. The downward component of the acceleration of block B is 1 meter per second squared. All right, for block A and block B, we want to draw the new free body diagrams and write out the algebraic form of Newton's second law. And then we'll worry about question Roman numeral 2. All right. So again, we'll start with block B. There's the force on B due to block A. I have the weight of block A. And the force of static friction is not big enough to cancel that out. Okay. Now we look at block A. I'm going to have the interaction partner to this force, the force on B due to A, which is going to be the force on A due to B. Force on A due to B. There is going to be a force of static friction down on block A, which I'm just going to call minus force of static friction. I've got the weight of block A. And I've got the normal force on block A to cancel out. And we are pushing with our hand on block A to the right. All right, writing out the algebraic form of Newton's second law of motion. Force of the push minus the force on A due to B. It's going to be the mass of block A times the acceleration in the x direction. Vertically, we have equilibrium. So the normal force on A minus the weight of A minus force of static friction down on A has to sum to 0. For block B, force on B due to A is going to accelerate block B to the right. So I have the inertia of block B times the x component of the acceleration. Now, in the vertical direction, I don't have equilibrium because it's an accelerate down. So force of static friction up comes into the plus sign. Weight, try to be more careful, x to the right, y up. Force of static friction up minus weight down. And I'm going to have an acceleration down. So it's going to be minus mass of block B, and then we know that is 1 meter per second squared, as block B is falling down. Is the magnitude of the force exerted on block A by the ground, in this case, greater than, less than, or equal to the force exerted on block A by the ground in the previous part, part C? Okay, and this force of static friction is now not as big, so the force down on block A is not as big. Less than. In our reasoning, block B is partly falling. not all its weight is supported by the ground. So the ground doesn't have to push as hard on block A and B as the combined weights of blocks A and B. Okay. Now, since B is partly falling, the normal force is going to be less than the combined weights. You imagine if block B were just in free fall, then it would have no impact on the normal force on block A. If block B were in free fall straight down, then the normal force on block A is just enough to cancel out the weight of block A. Calculate the magnitude of the force exerted on block A by the ground and show your work. So we're going to do the same steps as last time. We're going to figure out how big the force of static friction is, and then plug it into this equation and find out how big the normal force on block A is. So the force of static friction, move everything to the other side. I'm going to have, that is the weight of block B. That should be a B, and that's a B. Okay. So, force of static friction, I move everything to the other side. I'm going to have mass of block B, 10 meters per second squared for the acceleration due to gravity, and then minus 1 meter per second squared. Mass of block B is still 2 kilograms, and so this is 9 meters per second squared. It's going to be 18 newtons, less than 20 newtons in part C. Now we have everything to find how hard the ground is pushing up on block A. So the normal force on block A is going to equal the weight of block A plus the force of static friction. So 100 newtons plus 18 newtons is going to be 118 newtons, which, as promised, is less than 120 newtons. So since block B is partly falling, the ground is not going to push up hard enough to cancel out the weight of both A and B. It's canceling out all of the weight of A and part